apologize for being late. I was coming from a previous class where we were giving an exam. For some reason, they thought that we should give them the full 2 hours, or a full hour and a half instead of just an hour and 20 minutes. So I was a little late collecting the exams. So how are you doing? Not well, huh? How is the homework going? How's that test 2 treating you? Any questions about that? Is it going okay? Have you started? No? Start now. I feel like that's my my role in life now, is telling you to start now. If it's the project, I tell you start now. And if it's the homework, I tell you start now. And if it's listening to this lecture, I'm also going to tell you start now. Because we're going to talk today more about semantics. Oh, it's the wrong one. We're first going to talk about meaning representation languages. So today we'll talk about meaning representation languages and about semantic roles. And after this, then I will be gone on Thursday and Professor Black will be gone. So we're going to have a guest lecturer, Bob Frederking, who's going to come in and he's going to talk to you about compositional semantics and semantic parsing. Then we'll be back and we'll talk to you about discourse and pragmatics. Probably Professor Black will do that. But today we're going to talk about meaning representation languages, and in order to do that, it's helpful to start off with a little bit of a discussion about intension and extension in semantics. So there are 2 approaches to semantics that we might take. There are a number of different approaches, but this is one way of dividing things up. There's the distinction between intention and extension. Has anybody here ever had like a philosophy of language class or a semantics class? Any of the linguistic people? Anyway, if you so, you might have come across these terms. But basically, an intentional theory of semantics locates meaning inside of the words or inside of the sentences. It says, and so we look at the meaning in terms. For example, if we're looking at it decompositionally, in terms of the constituent parts, like these words have these semantic features and we put them together and we get this complex thing that has these other semantic features that we can derive from the semantic features of the parts. So we put together pieces and we locate the meaning inside of the words. So the words correspond to a meaning. So this is, and the pieces of meaning are basically inside of the words. This is in contrast to an extensional theory of meaning, which says that the meaning of a word or an utterance is the set of possible worlds under which that sentence is true. So it talks about meaning in terms of sets. So if you have the word red, for example, in an intentional theory of meaning, it might be that this is a color, that this is, I don't know, 255 R, 0 green, 0 blue, something like that. But in an extensional theory of meaning, then red is the set of all things in the universe that are red. And that's what red means. It's a set of things in the world. It's the things of which red is true. There's a predicate red that corresponds to the word red, and the set of things for which that predicate is true is the meaning of red. Does that make sense? So it's the same thing with the predicate hit. So if I say, I hit you, then the meaning of this is the possible worlds in which I took my fist and punched you with it. That's no possible world. Anyway, I would not hit you, but hypothetically speaking, that's what hit and I hit you would mean if we looked at the world extensionally. So the extension. So in this lecture, we're going to look at ways of representing the extension of verbs and of sentences. And we'll also look at semantic roles and how they relate to meaning representation languages. So we want to represent meaning. I mean, you might not want to represent meaning. Maybe you just believe in big neural networks and you don't want to have any meaning representation. You just want end-to-end. You just want to feed some data in and get an answer out. And you don't care what is happening inside. This is a perfectly legitimate point of view, but that's not the point of view we're going to be taking in this course. We're going to be actually talking about ways of representing meaning in an intermediate sort of way that are interpretable, that you can get at and look at. And to do this, we need meaning representation languages. We need some kind of formal apparatus for representing the extension of sentences. So what do you think would make it good, if you're trying to represent meaning, what kind of, and you're trying to represent extensional meaning, what kind of a system would be a good way of doing this? What are the desirable properties of such a language if you're trying to represent meaning? Can you think of anything that would make a schema for representing meaning better than another one? What is meaning like that could give us an idea of how to represent it? Is meaning just a mishmash of vectors? Well, it's kind of what we led you to believe last time. But when you're talking about language and meaning in language, what are you really talking about? Well, let's give you some ideas. So what kind of tasks might you want a meaning representation language for? So this kind of sits between what you do with parsing and word sense disambiguation and co-reference resolution, semantic role labeling, and then non-linguistic domains. So this meaning representation forms the bridge. And this is useful in tasks like answering essay questions on an exam, or deciding what to order in a restaurant, learning an activity by instructions, making an investment decision, recognizing whether you're being insulted. That's actually the most important one. I find that I'm insulted constantly, and without natural language technologies, I wouldn't know when I was being insulted. Since we built this insult classifier, I've been so much better informed. So what would be good as a representation to help us do these things? What kinds of properties should such a representation have? Well, one is verifiability. So we should be able to determine the truth of our representations. So if we ask, does Udupi serve vegetarian food, we should be able to know whether something like serve Udupi vegetarian food is in our knowledge base. We should be able to verify that. We should be able to verify the relationship between the meaning of the sentence and the world as we know it. So the world as we know it is represented in a knowledge base, and we should be able to query the knowledge base against sentences that might come up. Another desirable quality is unambiguous representation. So for each meaning, there should be one representation, semantic representation. And regardless of how many linguistic representations there are. And each meaning representation, each semantic representation should mean a different thing. So if you have, so sometimes people say, well, we could just use natural language to be our meaning representation language. We don't need any fancy meaning representation languages. But natural language doesn't have this property. So if you say, let's eat somewhere near campus, this could really mean two things, right? So it could mean we want to eat at a place near campus, or that we eat places. Who eats places? I eat places. So our MRL must capture exactly one of these meanings. It should not capture both of those meanings. So so if we encode, each of these should have a separate representation, right? Another desirable property is canonical form. So these all have basically the same meaning, even though we're expressing them differently in natural language. So these should have a single semantic representation. We should have a canonical form that's the same for all of these. Finally, there are other properties that are also important. These are inference, the ability to do inference over sets of statements or sets of sentences, and to have things like variables, and to have an expressive language. So these are three different things. So first, can vegetarians eat at Mad Max? You know, you want to be able to know that if in your knowledge base it says that vegetarians eat vegetarian food and that Mad Max serves vegetarian food, that you can infer, therefore, that vegetarians can eat the food at Mad Max. And one way of doing this is with variables. So you could have you could make a query that says something like serve X vegetarian food, and that should return all of the X's such that they serve their restaurants that serve vegetarian food. Finally, we want a language that's expressive enough that we can extend it to new domains, that is not tied completely to a particular domain. So you want to be able to say things like Delta flies Boeing 737 straight into the Brown, or I mean, from Boston to New York, and that is expressiveness. So one thing that we're not going to account for with our meaning representations is figurative language. We'll focus on basic requirements for meaning representation. And we'll ignore things like Ford was hemorrhaging money or I could eat a horse. Or we'll treat them literally, like Ford was bleeding money, or I am able to consume an equine. So what do we want to represent? It should let us encode at least 3 different things. So objects, people, restaurants, cuisines. You know, I didn't come up with this whole, my slides are partly my own, but they have a long pedigree going back to this guy named Noah Smith, who was one of the people who originated this course back many years ago. And he was very into restaurants, and so he always used restaurants as examples. But I updated it with restaurants that still exist, because a lot of the restaurants that he included are now defunct. But that's why there's all this talk of restaurants and cuisines. It's an homage to Noah Smith. Also, properties of objects, like pickiness, noisiness, spiciness, and relations between objects. So, whether Oishi Bento serves Japanese. This is all tied together by the knowledge base. So the knowledge base contains everything that we know. And the nice thing about the knowledge base is that, like a paper bag, we can reach inside it. We can query it. So some people in their projects, they basically use a knowledge-based approach. So you go and extract a bunch of relations and put them in the knowledge base, and then you can use those to make questions and to answer questions. So let's talk about some specific meaning representation languages. Do you have any ideas of what kinds of languages might be good to do the sorts of things that we're talking about here? Any candidates that you would suggest? Well, you look like you're going to say something.
I was thinking probably not Turkey.
Probably not.
Not Turkish.
Not Turkish? Yeah, probably not Turkish.
Or anything that many affixes.
Yeah, probably not a natural language, right? Yeah, it would probably be some kind of mathematical representation, right? And you could think of different kinds of mathematical or logical representations that you could use to represent meaning in this way, to represent the extension of sentences. So here are some examples. What is this up at the top? Who could read that to us? In fluent logic. This is there exists an X and a Y such that having X and haver, speaker X and having YX and car Y. So what does that mean? So this is, what kind of a representation is this? What sort of language, in a way, is this? same language really that we use to do mathematical proofs, right? It is first order predicate logic. Who here has done something with first order predicate logic before? Okay. So how do you like it? What are your feelings on first order predicate logic? It's fine. It's not fun. You don't think it's fun. Terrible. It's lovely. Anyway, but it has certain limitations when you want to talk about things in time, for example. It's not so easy. So we have one of our candidates is first order predicate logic, or FOL. So other candidates are what are called description logics. And these are represented here in 3 different ways. So here we have a having event, which has a haver and a had thing. The haver is the speaker, and the had thing is a car. So what does this mean? If we were to give a corresponding English sentence. So speaker means the person who's speaking it. So that would translate as I, right? So I, and it's a having event. So the verb that encodes the main predicate is going to be have, and the thing that is had is a car. So the English translation of this is I have a car. I have car. I have a car, right? And that's the same thing that this means. Here we could say speaker, car are related by a possessed by a relation. So this is like a triple. And this is a slot filler representation of the same thing as this. So we have a having event. It has, so this kind of having frame has a haver, which is the speaker, and a had thing, which is the car. So let's look first at first order logic. So in first order logic, we have entities, things, like the porch and Udemy. We have functions that take entities and return something else. And we have predicates that take arguments and return either true or false. So these are like booleans, and these are other functions. So we can take sentences of English and we can translate them into first order logic. Or we can take first order logic and we can translate it back into English. So who could translate the first sentence here for us? The first statement in first order logic. Yes.
I have $5 and I don't have a lot of time.
Yes. I have $5 and I don't have a lot of time. What about this one? Yes, what does it mean?
Every person has $5.
Yeah, everybody has $5. Everybody has $5. And what about this one? It's a little harder. Somebody else. Yes.
There's some restaurant that someone with $5 hasn't visited.
Not $5, but yeah.
Oh wait.
We did say above. We did say above.
What?
We did say above that everyone has.
Who has $5? So, by modus ponens. Anyway. Just kidding. Yeah. So, if we translate first order logic into semantics, then basically nouns correspond to one place predicates. So restaurant X is true if X is a member of the set of restaurants. adjectives also correspond to one-place predicates. So vegetarian X is true if X is a member of the set of things that are vegetarian. Verbs correspond to one-place, two-place, or three-place predicates, depending if you're doing something fancy called Neo-Davidsonian semantics, then they correspond to even more. So you can have dine, eat, and give. Dine would be a one-place predicate, eat would be a two-place predicate, and give would be a three-place predicate. So one fancy thing that you can do with first-order logic is you can use modus ponens and forward chaining. So if you have in your knowledge base the statement that Udupi is a vegetarian restaurant, and that also the statement that for all vegetarian restaurants they serve vegetarian food, you can therefore conclude that Udupi serves vegetarian food. And basically, you can do this automatically. So every time you add something to your knowledge base, you can go through and apply modus ponens wherever it will apply, and you can learn all sorts of things and make all kinds of inferences that are logically implied by the things that you put into the knowledge base. So you can do some kinds of inference this way. It's actually quite powerful. Can you think of any disadvantages of this? What's going to happen to your knowledge base? Yes?
It's gonna get very big very fast.
Just get very big, very fast, because you can have exponential growth actually in the size of the knowledge base, and a lot of the facts that you infer are not going to be of interest. They're going to be sort of trivial. So this is a strength, but also a weakness. So here are advantages of first-order logic. It's flexible, it's very expressive, it's widely understood, and it's widely used. So these are all nice things. Can you think of any disadvantages of it? Like, if you're trying to make a computational implementation of a system that uses first-order logic, what might be problematic about it? Yes?
Potentially creating the names of the predicates. Potentially, like figuring out the format, whether it's 1, 2, or 3, like a verb.
Yeah, so the fact that it's expressive actually adds somewhat to the complexity of dealing with it, right? Any other things? So as a data structure, what does a knowledge base in first-order logic look like? Yes?
Is it that it's all true and false? Like, do we have anything that says maybe or possibly any models?
We don't have modals. So that's actually a problem. That's actually the fact that it's not a modal logic means that you don't have any way of dealing with probability or possibility or any other modal property. So that actually is a problem with first-order logic when you're trying to deal with natural language in a natural sort of way. It's not the one that we'll deal with here. But basically, in first-order logic, it's very flexible. Implementing it computationally is well understood, but dealing with inference in first-order logic is computationally quite complex. And modal logics are even worse. So yes. So we have description logic. That's the next step here. These are less expressive than first order logic, but they're computationally much more tractable. So these are basically slot filler representations. So you have an event that's a having event, it has the slots haver and had been, and you can fill those in. So this is more restricted than first order logic. Along with this, you often will divide your knowledge base into two parts, a T box and an A box. A T box contains knowledge about the categories or concepts in the application domain. So it's like these general statements about the whole domain. Like all bistros are restaurants. All restaurants are businesses. The A box is facts about individuals in the domain. Like Udupi is an Indian restaurant. Or Noah likes expensive restaurants. So we've got the T box and the A box. And this architecture allows for some kinds of more efficient work. So you have basic relations that exist that you can capture among elements within a description logic. And one of the most important of these is subsumption. So if we say that at Udupi, we have in our A box a statement that Udupi is an Indian restaurant, and we have in our T box a statement that Indian restaurants subsume restaurants, are subsumed by restaurants. Then we could reason that Udupi is a restaurant, through subsumption. We also have access to negation and disjunction. Now, here are some advantages of description logics. What results when we use a description logic to describe a domain is essentially an ontology. And ontologies are fairly well understood. So it's a graph. A graph where edges are subsumption and negation and union operations. And so you can reason about it like any other ontology. And it has a sort of intuitive quality to it. It's also, can you think of any other advantages? You should compare it with first order logic. Well, for one thing, the kind of representation that you need to do it is much simpler. You just basically need nested dictionaries, and sets of nested dictionaries to handle the kind of slot filler relationships that you have in description logic. And in some cases, you could get by with just, in some description logics, just with triples. A triple store is a kind of description logic. So what we're going to talk about next is kind of the space between meaning representation and this step here where we have parsing, WSD, corref, semantic role, labeling. We're going to talk about actually semantic roles. So it kind of goes with this. This is where compositional semantics and semantic parsing go, which is what we'll talk about on Thursday. But in order to get there and to understand semantic role labeling, we have to talk about semantic roles. So that's what we'll talk about next. So what is a semantic role? What is my semantic role? I am an agent. And you are a recipient. So, so if you look at a passage like this again is the work of Noah Smith. So that's why it's about Noah. Even though Noah was is one of the most intensely anti-religious people I've ever encountered, he still uses biblical examples to contain his name. So Noah built an ark out of gopher wood. He loaded 2 of every animal onto the ark. Noah piloted the ark into stormy weather. When the skies cleared, all rejoiced. So we've got a number of different noun phrases here. And they have different relationships to one another. And one way we could look at this is in terms of grammatical relations. So Noah is the subject of built, and ark is an object of built. And of is a preposition with gopher wood as its object. But this only tells us about the syntactic structure of the sentence. It doesn't tell us about the semantics of the sentence. So in order to get there, we first have to identify the noun phrases, but then we can note that if we make a paraphrase of this sentence, Noah built an ark about gopher wood, we can switch around what the grammatical relations are, like subject and object, and still have the same meaning. So we could say an ark was built by Noah. It was made from gopher wood. Or Noah constructed an ark with wood from a gopher tree. Or using gopher wood, Noah managed to put together an ark. Or Noah built an ark. In all of these sentences, Noah, even though Noah isn't always the subject, Noah is always the one constructing the ark. So we want some invariant way of expressing that Noah is the one that he is a volitional actor acting on something in the world. So what is this thing, this invariant that we want to assign to Noah? What do we want to call Noah? Well, there are a couple of good answers to this. Linguists, for the most part, would say that Noah is an agent, and they would assign the semantic role agent to Noah. Linguists who do frame semantics would say, well, it's more specific than that. This is a building event, and Noah is the builder. But in either case, then there's a role that's assigned to Noah that is the same through all of these sentences, even though the grammatical structure changes around. So it's part of the meaning. It's a semantic role rather than a grammatical relation. So here are some traditional semantic roles. We've got agent, like Noah. Patient, or theme. These are things that are affected by the action of an agent. So an agent does something to something else, and the patient or theme are affected by it. We've got a force, experiencer. So an experiencer is like if you say, I love this class, and I hope you're saying that right now, I love this, no, then you're an experiencer. If you're saying, I hate this class, then you're a jerk and also an experiencer. This class in those cases would be a stimulus. And if I said, I gave the information to you, then you would be a recipient, I would be a source, or I took the book from the box, then that box would be the source. Goal, like I went to GHC would be the goal, and so on. So these have their use, and they're used sometimes in annotating natural language data, but they're not super widely used in NLP. In NLP, people tend to use finer grained roles that are easier for non-linguists to annotate with. But understanding traditional semantic roles is helpful in understanding semantic roles generally. So if I have this sentence here, David threw the midterms from Pouch Bridge to the hillside below, crushing the daffodils. Then David is the agent, the midterms are the theme, Pouch Bridge is the source, and the hillside below is the goal. I didn't actually do that, but I thought about it, but only after they were scanned. So there's another way of representing these things in first-order logic that is convenient, and that's what's called a neo-Davidsonian representation. So rather than having a single predicate for throw that has a place for agent and patient and source and goal, you could say that there was an event. So this is unwieldy, because then you have to, if any of these is missing or an extra one is there, you have to have another predicate throw. And that's very ugly. But what you can do is you can say that the event is an entity. And then you can say that the event has an agent, David, a theme, midterms, a source, Pouch Bridge, and a goal, hillside. And then if we take the passive of this and leave out hillside, we still have basically the same representation. So in semantic role labeling, this is an important task in NLP. And the input to this task is basically a sentence or a paragraph or a document, and the output is a labeling such that for each predicate, basically for our purposes, each verb, and this might already be identified or they might not in the input, then we want labeled spans indicating each of its arguments. And the label will be the semantic role, thus the term semantic role labeling. So how is this different from dependency parsing? Easier or harder than dependency parsing? So dependency parsing uncovers syntactic structure. It uncovers grammatical relations, like subject and object. But these are different from semantic roles. And basically, in order to do semantic role labeling, you usually do dependency parsing first. And then you have some way of going from that dependency parse, which tells you what the subject and the object and so on are, from there to get to the semantic roles. So you have some kind of machine learning model that learns that in this kind of situation, the subject is the agent. In this kind of a situation, the subject is the patient, and so on. So semantic role labeling is much harder than parsing, than syntactic parsing. So, for example, we have these predicates: built, made, constructed, put together. And they have these arguments. So built, Noah, and an ark, Noah, an ark, Noah, an ark. So semantic role labeling is the task of identifying these arguments, labeling them with semantic roles. So one of the most important resources for semantic role labeling is PropBank. Who here has heard of PropBank? Nobody's heard of PropBank? You haven't, literally. No, just kidding. That's FrameNet. PropBank is basically a chunk of the Penn tree bank with propositions annotated. So basically they did semantic role labeling by hand on a section of the Penn tree bank. So the predicates correspond to verbs. They basically went through all of the verbs and assigned and said, okay, this verb takes these arguments. And they called them arg0, arg1, arg2, where arg0 is the prototypical agent or prototypical subject, meaning that it's the most agent-like argument. And arg1 is prototypical patient, and then the others are sort of arbitrary. But you have arg0, arg1, and so on up to argn. So they went and they built a lexicon. For each of the verbs, they came up with these frames. And then they had people go and annotate the text according to this lexicon that they built, the linguists had built. And the annotators were not necessarily linguists or not necessarily good at their job. But they went through and identified in Penn tree bank every time one of these verbs occurs and what the spans of the arguments are. And we use this as training data and test data for semantic role labeling. So it's widely used. So for example, agree in PropBank has the following arguments. Its arg0 is the agreeer. Its arg1 is the proposition to which the agreeer agrees. And arg2 is the other another entity agreeing. So if you say, usually John agrees with Mary on everything, then Mary is arg2. Whereas if you say the group agreed it wouldn't make an offer, it wouldn't make an offer as arg1. Here's a more complicated example. This is fall in the sense of move downward from PropBank. So arg1 is the logical subject, the patient, the thing falling. Arg2 is the extent of the fall. Arg3 is the point that this falling starts at, and arg4 is the ending point. And then argm loc is the medium through which something falls. So any of these cases, so if you say sales fell to 251.2 million from 278.8 million, then you have a fall sales being arg1, 251 million being an ending point, and 278 million being the starting point. So this is how PropBank works. They just went and annotated a whole bunch of Penn tree bank in this way. So then you can go to the trees in Pantry Bank, and you can learn paths between a span. So this NP corresponds to arg0 in this particular case. So we can learn a path up to S and down to the verb that encodes the predicate. So if you can learn all of these paths and learn what these paths are like, you can predict, you can be given trees that don't have these annotations, and you can figure out what the likely annotations would be. So there's another resource that is very important in doing semantic role labeling, kind of the competitor to PropBank, and that is FrameNet. Has anybody here heard of FrameNet before? So FrameNet, like me, comes from University of California, Berkeley. Because I know a lot of the people who worked on FrameNet, then I have a bias towards it, and I find it somehow better than PropBank. But this could be a bias on my part. So basically, the idea in FrameNet is you have frames. Frames are schematic representations of situations that can involve different participants and other conceptual roles that are not necessarily concrete entities. So you imagine a particular frame, like a buying frame. And a buying frame must have a buyer. It must have the thing bought. It can have a recipient for whom something was bought. It can have a price. It can have a number of other kinds of slots within this frame. So the interesting thing is that the frame for buy is going to be the same basically as the frame for purchase. And this is important because in FrameNet, it's not the verbs that are the first class citizens. It's the frames. It's the schematized representation of events or situations. So this involves slicing the universe up in a little bit different way. That captures some generalities that are missed in the PropBank kind of approach. But it's harder to annotate and more expensive to annotate, so FrameNet is not as big. There's not as much annotated data for training and so on. And then another interesting thing is that frames can center around words that are not verbs, which is different from PropBank and gives FrameNet some flexibility in terms of identifying roles for nonverbal predicates. So here's an example of a frame. This is change position on a scale. That's one of the frames. And it has core roles like attribute, difference, final state, final value, initial state, initial value, item, and value range. And then some non-core roles like duration, speed, and group. And you have all sorts of, so we talked about the PropBank definition for fall, right? So fall would be one verb that fell into this frame, or that could trigger this frame. But descend would also be something that could trigger this verb, or ascend. fact, advance, climb, decline, decrease, diminish, and so on. And nouns like decline, decrease, escalation, explosion, fall, fluctuation. The adverb increasingly. So all of these could invoke the change position on a scale frame. So it's generalizing over sets of verbs and sets of nouns. At the same time, the roles are very fine-grained, like in prop bank, except they're given more informative names. So here is FrameNet website. And if we go here, let's see. We can pick frames. Anybody have a favorite frame? Abandonment. That's the first one. So, hopefully this doesn't describe you as children. So in this, the definition is that an agent leaves behind a theme, effectively rendering it no longer within their control or of the normal security of one's property. And some advantages. And so it lists off core roles and non-core roles. And then, let's see, how do you get to the examples? Oh, here. Okay. So here are different verbs and nouns that trigger this frame. So abandon, abandoned, forget, leave. So let's look at cases of forget that trigger the abandonment frame. When I tugged back a sleeve, the wrist was naked. Forgot my watch again, and both hands chapped and rough. Okay, so in this case, forgot my watch is classed plausibly as an instance of the abandoned frame. So any questions about this? About FrameNet? So both of these are used, both FrameNet and PropBank are widely used in training semantic role labeling systems and evaluating them. And which one works better really depends on what you're doing. If you are interested in the frames themselves and having a more general semantic representation of what is going on with the different roles, then FrameNet actually provides more information. If you want something that has more data, more training data, then PropBank is better, basically, because PropBank is bigger, and they've been Martha Palmer, who is the kind of instigator behind PropBank and other associated projects, is very good at getting money, and so she's been able to fund a lot of work on PropBank and a lot of development. The FrameNet people, like the principal guy died, and the successors have not been as good as raising money. So PropBank probably has a better, there's a better future in terms of development of future versions. But yeah. So any questions about anything? You seem very tired. Very tired. So I'm going to let you go early and not pester you with more questions. So get 15 minutes of rest. And prepare for your next class.